Today we're going to study damped oscillation in an RLC circuit. This R stands for resistance, L for inductance, C for capacitance. So let's see, we have, here is an inductor. We have an inductor. We have a capacitor. And then we have a resistor. So this is an RLC circuit. This is the inductor L. This is the capacitor C. And this is the resistor R. Now let's look at the energy. If you have a current in the circuit, you're going to have energy in the capacitor. And that energy is stored in the electric field. You're going to have energy in the inductor, and that energy is stored in the magnetic field. And this energy will dissipate through this resistor. So this resistor takes out the energy in form of heat. So what happens is, we look at this energy here that's stored in the capacitor inductor, which is U, is equal to 1/2 Li squared. This is the energy stored in the inductor. And then we add to it the energy stored in the capacitor, which is Q squared over 2C. Now, this change of energy, okay, is going to show up in the resistor, okay, because this energy here is given to the resistor, and the resistor, it comes out of it at energy per unit time. So every time you have energy coming out in form of heat and radiation coming out of the resistor. So if we look at the change in the energy for these two, for the inductor and the capacitor, we put here du. This is the energy that we have stored in the system, okay? It's in the capacitor and the inductor, not in the resistor. The resistor, only the energy just comes out of it. So we put here, this is with respect to time, du dt is equal to 2 over 2 Li di over dt plus 2 over 2 Q over C dq over dt. Now these two cancel that 2, and this becomes Li di over dt plus Q over C, and dq over dt is I, so I put I there. Okay. Now, if we look at the resistor, that energy here is going to come out of the resistor, so I put here du over dt. This is a power. The energy is going to come out in form of energy over time, which is power. So the power that comes out of the resistor is Ri squared. Okay, is the resistor times the current, resistance times the current squared. But the energy, we lose in energy through the resistor, so put negative sign. If you look at here, you can say U final minus U initial over T final minus T initial. So T final minus T initial is positive because we increase in time, we moving forward in time. So T final minus T initial is positive. But U final, so the energy is gonna decrease because we lose in energy through the resistor. So this should be negative. This is negative. So that's why we put here minus Ri squared. Okay. Now, this power here that came out through the resistor is equal to the power given by the inductor and the capacitor. So I put here, I put Li di over dt plus q over ci is equal to minus ri squared. Look at now. Look at the current. I have the current here, I have a current here, and then I have this current. So my equation can change now. I put L di over dt plus q over c plus ri is equal to 0. Now we know that I is equal to dq over dt. And then we put it here. So I put L d second derivative dt squared q plus r dq over dt, because remember I is dq over dt, plus q over c is equal to 0. Let's divide by everything by L. So I put d squared q over dt squared plus r over L plus q over LC is equal to 0. Okay? Look, this is a second order differential equation. We have here second derivative, we have the variable. So what I can do, let me just here, I have to watch what I did. I made a mistake, I'm sorry. I have r dq over dt. Yeah, I made a mistake. Let me fix it. I divide, here I have r dq over dt plus q. So I divide this by L, and I have to put here dq dt. I forgot to put that dq dt. When I divide by L, I have to put that here, and this is okay. So now I need to look for q. So I'm gonna do a trial solution. Put q is equal to some constant a, e, r, t. This is a differential equation. By using this change of variables, I'm gonna make it algebraic equation. I solve it using algebra. I'm gonna change this equation from differential to algebraic by using this. This a is a constant, and this r is a constant. So if I take the first derivative, so I put dq over dt is equal to a r e r t. Second derivative, I put d squared q dt squared is equal to a r squared e r t. Now I have this second derivative, first derivative, we put them back into the differential equation. So let's put this back here. So I get a I have a r squared e r t. Took this, put it there. Plus r over L. dq over dt is this one. I put a r e r t plus q. I put a e r t over LC equal to 0. Now a is a constant, it's not equal to 0, so we take it out. This exponential is not equal to 0. It can only be 0 when t goes to minus infinity. Okay, so this also is not equal to 0. So what we have left, we have r squared plus r over L r plus 1 over LC is equal to 0. Look at this. The variable here is r. What we're looking for is r. And before we had differential equation, look now we have just algebraic equation. We can solve it just using algebra. So this is a second order equation or a quadratic equation. So I put here R1, 2, comma, 1, comma, 2, which means we can have two solutions. So I put here minus R over L, this is B, plus or minus square root. I put R squared over L squared, okay, minus 4, I put 1 here, A, and then I put C, 1 over LC. This is over 2. Okay, so I just use a quadratic equation. This 2 is going to go up here, so I put here minus R over 2L plus or minus, this 2 is going to go up there, so I go square root of R squared over 4L squared minus 1 over LC. These 2 went up there, became 4. Found that 4 cancel each other out. These 4 cancel that 4 after it got inside the radical became 4 because it's 2 now. And these 2 here went up there, went inside the radical, become 4, so it stayed there. There is nothing to cancel with. Now, remember this is, I put here R1, 2. We have that plus or minus. Remember this R here, this R that we found? We have to put it back there. We have to put it here because remember we're looking for Q. But before I put it back there, I need to do one thing because I want to make it, I want to have an I here, an imaginary number. So when I put it back here, I have exponential of imaginary number is going to give me cosine and sine. So what I can do this. This is a trick. I can put here minus R over 2L plus or minus square root. I put a minus here. And then I put 1 over LC minus R squared over 4L squared, close bracket. You see, I just pull out this minus. So this minus here, if it comes out of the radical, becomes I. This minus is equal, minus 1 is equal to I squared. So when I squared comes out of the radical, becomes I. So I can just put here, I can write minus R over 2L plus or minus I, and then I have 1 over LC minus R squared over 4L squared. And here is now that R2. So now what I need to do, I need to take this R and put it back in there. Okay, I need to put it here. So I need new page. So let me get new page. So now I need to go find that Q. I put here Q is equal, this is what we had before. Q is equal to A. Remember, it's here. It's there. There. So Q, let me take this paper out. Q is equal to A. Oops, I'm sorry. And then I have to make this exponential. A, and then I have minus R over 2L. I'm using this. And then I put plus or minus, and then I have I square root of 1 over LC minus R squared over 4L squared. And remember, I have time times T. because if you see here, I have time there. See? So I put t. So now this is equal to a e minus r over 2lt, and then I put times e plus or minus I, and then I put square root of 1 over lc minus r squared over 4l squared times t. So I opened it. Exponential of the sum is the product of the exponentials. Now, what should I do now? Remember, this is q. Look at here, we have this exponential. This exponential plus this radical is equal to cosine. Remember, maybe you did this in high school. E I theta is equal to cosine theta plus I sine theta. You see, this is equal to that. Now, we need to open this, and then we're going to get the cosine and sine. But look what we have in front of the sine. We have that I. We have i's in front of the sine. This I is a complex number. It's imaginary number. So we don't need to add the sine because that term, the sine, has an imaginary number in front of it. This is physics we have in this circuitry. We have to deal with the real answer or real solutions. So we need to drop the sine. We keep only the cosine because the sine has that imaginary number. So our q will change. We'll have a, okay? We'll have a, and then we have e minus r over 2l t, and then we have cosine of 1 over lc minus r squared over 4l squared, and then we have t. This is the behavior of the charge in the circuit RLC when it's damped. Now, what do we mean by damped? You see that the resistor is taking the energy from the system. It's like damping the system. The system tried to oscillate. The circuit tried to oscillate, but that resistor is slowing down the oscillation. It's like you have some block connected to some spring oscillating, and it's in the water. If it's the water, it's going to oscillate slowly. So the water is a damper. It's going to damp the oscillation. The same thing here. This resistor is damping the oscillation. Look what happened here. We have R there. You see that R? This is, we have some new, this is actually, remember, it should look like this, cosine omega prime t. This is a frequency, or 2 pi times the frequency. And look, we have that R there. If R didn't exist, we will have that omega that we know, which I showed you. I put here 1 over square root of LC. If R didn't exist, if R is equal to 0, okay? But now we have R. That R, we're going to have different frequency, so which means I have to use omega prime, not omega. So my Q is equal to A. I have here E minus R over 2L T, and I put cosine omega prime T. Now this is Q in the circuit. Now we have two things are interacting here. We have the cosine of T, and then we have the exponential of T. Remember, the cosine tried to oscillate. It goes like this, try to oscillate. The exponential, this is negative sign, tried to go down like that. One tried to oscillate, the other one goes down. So what's gonna happen to Q is gonna, well, before, let's wait and see what's gonna happen to Q later after we find this A here, this A. I put here at time t equal to 0. What will happen? Cosine 0 is 1. Exponential 0 is 1. So we have Q is equal to A, and then we put here Q0. This is some charge that we have in the capacitor at time t equal to 0. Okay? So what we can do, we can say Q is equal to Q0 E minus R over 2L T cosine omega prime T. So this is the behavior of the charge in the circuit. Okay? So let's see what's going to happen. I put here Q. This is Q here. And then here I put time. You see, this one tried to oscillate like that. Cosine tried to oscillate. But this one is actually, this one is going to 0 faster than this one. This one is just, this is trying to kill cosine. This one is trying to oscillate, but this one is kind of depressing it, suppressing it. So I go something like this. I have these things that go like that. And then I have this cosine 0. I put 1 like this. And then it's going down like that. It's getting suppressed by these curve here. This is here. I put E minus R over 2L T. And this one was cosine omega prime T. So this one is trying to oscillate, but actually this exponential decay, we have a decay here. So it tried to suppress it. So the thing will keep on oscillating and getting weaker and weaker until it vanishes. So we'll have some situation, let me see, like that. So, and I put here Q. So who is damping this circuit is the resistor. And where is the resistor? Look at it, it's there. You have a resistor. If, let's see what's going to happen. If R is equal to 0, if we don't have a resistor, we will have Q is equal to Q0, exponential 0 is 1, and then we have cosine. What is omega prime? Let's look at omega prime. Omega prime is this one. If R is 0, we just have 1 over LC. So we just have omega T. And look at this. If you plot this, it's going to go like this forever. Go like that forever. Okay? And I put here Q0. So, and here I put time. So Q will just keep changing the, coming to the capacitor and then leaving the capacitor, coming, leaving, coming one direction. It'll be oscillating back and forth, back and forth. But because we put that resistor, the resistor damped the oscillation. And then we start losing the charge, losing it because the energy is coming out per unit time through the resistor. So the power, we're losing power to the resistor. The resistor keeps radiating power, radiating, heating up the wire, radiating, and then giving heat to the space, and then after a while there is no more current, it stops. Okay, so this is the damped oscillation in an RLC circuit.